nutshell. Here I'm considering to have the vectorized function to make our program slower. So in that case, what happens that generally whenever we do have the vectorized operation, vectorized function with us, like loop works on number of data sets. Vector also work on number of data sets. So whenever we have the vectorized function, then we should avoid the loop in that case. So here, like we can see how we use the vectorized function. So the idea that one should avoid loops wherever possible in R using nested vectorized functions like those in applied family. It's quite widespread in some quarters. So like where we have many functions discussed, we have array apply, then other than that s apply, and other than that t apply, which basically like implement on the whole data set. So this is what, like whenever we have the vectorized function, which are whatever we have discussed in this unit, so we prefer to use that rather than the for loop. When we wrote the total function, we mentioned that R already has some to do this. Some is much faster than the interpreted for the for loop, because some is coded in C to work with a vector number. So whenever sum is basically it works on a large data set, or we can say on a complete data set. So many of our functions work the way loop is hidden from us in C. So somehow we usually avoid to use the loop in the R. Like this is the basically we can say in the nutshell. Here I'm considering the example like x is equal to run if this condition is there, y is equal to numeric length function I am calling here. For k in sequence along x, yk is in x. We are basically calculating the sign value of the my for each and every value in the x. So to time this, we can wrap the vectorized part in a call to a system dot time. So in the like what I do, I'll put all this part like we can say all this part in the like system dot time function. So here you can see this is the line and this system dot time, this is it. So what time it will take here now for executing it for each and every operation, like I am calculating it, like it is taking 0.116.004 system and 0.12 to elapse. Then if I call the z directly, which works on the vectorized function, this is how we can work it. So it will take the time 0.032, 0.000 and 0.034. As you can see the difference here in the time. See here it is 116.034 here I am having this. So in that case, we can be sure that if we use the vectorized function, so basically it makes runs our program very fast. Then we have another this dot argument. Basically, whenever in our function, when we are not aware in advance, like how many arguments we are going to pass in a function, then this symbol we use. So there is a special argument in R known as this argument, which indicates a variable number of arguments. So this we didn't have in C language. So this is what, like, this is the flexibility. Whenever we are not sure how much data, how many arguments we are going to pass in the function, then we use this symbol. Okay. So for example, a custom plotting function may want to make use of default plot function along with its entire argument list. The function below changes the default for type argument to the value. The original value was p, and it is for I. So my plot function x comma y, the coordinates we are passing for the plot, then type is equal to I, then dot. So this is that we can it is giving us the flexibility to pass more arguments in this function. So this I am using plot this xy type, and any number of plots we can pass in the plot function. So generic function use so that extra argument can be passed in this method. The argument is necessary when the number of arguments passed to a function cannot be known in advance, as I already told you. So this exactly works like paste and cat function. Like we are using the concatenate function types and space, like we are adding more arguments. So here you can give the more arguments over there. So our space function this set collage. So null it will return. Then our cat. Then further we are adding some more argument in this function. So this is exactly works like the paste and the cat function. So argument coming after the argument, like one catch with this is that any argument that appear after this argument, list must be named explicitly and cannot be partially matched or matched positionally. Okay, so in that case, sometimes we got some confusion got created like this. Like sometimes the sequence gets changed. So our space function this, like we are using the space over here and collapse null. So with the paste function, the argument STP and collapse must be made explicitly. In full, if the default values are not going to be used. So how it will work? Paste A, comma B. Then these are the arguments I am passing, and separator will be the colon. So this is the way it can get placed. So you can add any number of arguments over here. Then if we don't specify the set argument in full and attempt to rely on partial matching, we do not get the expected result. So like we have to use here, like for example, like I am using the function here, this, and I am using SE here. So this will be placed. So these are considered as the three arguments which are dot dot dot, which are the part of dot dot dot. So it is giving you the output A, B, and as it is column. But if you are using the SCP over here, so whatever you are passing, A, B, C, D, any number of arguments you can pass here, and those all will be separated with this A, colon, B, colon, C. So you will get this type of output. So whenever we are not very sure how many arguments we are going to pass, we use this argument. Okay, with this your third unit is over. If you have any query, you can discuss it in the OSI session, and you can mail me your queries on ankita.mendiratha@scdl.net. Now I am going to start the new unit, which is basically the unit 4, which is mathematics in R. This is very easy to understand actually. Like we are already using the mathematical functions, and R provides us many much flexibility. Like R is basically designed for the statistics, so obviously it includes all the statistical functions, also string functions also that we are going to use in the understanding the coming units. And like all these functions are used in R. So we will have a quick recap of the same way. The function is called the same way you pass the argument over there. One way we have learned to pass the argument. So this is it will be used in the similar way. So if you know how to use these inbuilt functions, you will not face any problem in using it. Just we need to find out where to use which function. So understand the different arithmetic function and its uses, and explain and use the statistical and probability distribution function. Okay, so here are some numeric functions, and in your SLM there are many numeric functions are given. I'm going to explain the sum of here, like ABC x. The argument you are passing here x, which will give you the equal to 100 square square root, sorry, and in the case you will get the 10. Ceiling or ceil function, like ceiling, like it will basically round off the number you pass over here, and truncate the extra decimals, like ceiling 645, here you get 956, so it will return you 646. So this will be the return value. So we have to store this return value also in some variable. Then ceiling minus 10.28 will return you to minus 10. Then floor will return you like the base value used to return the largest integer value, which is not greater than or equal to x. So what will be the floor value for this? Like floor 645.956. The floor value of this will be the 645, and the floor value for this will be the minus 11, because it is a negative number. It would be the positive number like 10.28, so it would have returned you 11. So now the next one is the, so it would have returned you 9. Then truncate to basically truncate the extra decimals and all that. So we are working on a vector here. Truncate 1.234, it will return you 1. Then 2.342, it will return you 2. Then you will get the minus 4. Then minus 5 you will get, sorry, 5 you will get, then you will get 12, then you will get minus 14. So this is the like extra decimal part will get truncated. Then other than that, like there will be the rounds, like where will whatever the first argument you are passing to, like which is like the number. So how many points you need to round, how many digits should be there. So you need to do that. So like 1.25 digits you are passing with the 0, so it will give you 1.25. It will not round it. Then obviously it will got rounded if there was 0.9, so it would have returned you 1.126. Then round C, all the values will get rounded, so it will work on a whole like we can say vector. So this is 1.2 or 3 digits 2 you are passing. So up to the 2 decimal you will get it. So 1.23, then after that 2.34, then you will get here the 4.56, then you will get 5.67, yes. Then you will get here 3, 4, 5. Then so there is, I'm not going to teach you here how to round the figure. Just up to the 2 decimals you will get it. Then other than that, here is the signage. Like if the values are like similar to the round function, but digits argument in this function denotes the total digits, not the digits after the decimal. So that is the difference between the round and sign it. So in that case, 4 digits complete you want, so it won't counted after the decimal. It will count the complete 4 total 4 number digits. So it will give you 125.2. Now, similarly, there are other mathematical functions also which you can go through in your SLM. So these are the direct functions. Yes, you need to learn somehow the syntax, like how many arguments you are going to pass, and you that will be like all that is a basic understanding, and like we can say. So in that case, what happens, for example, if I am going to pass the rounds, so obviously I need some number, like I'll have to pass the number and how to up to how many digits I'm going to round. So this is a basic understanding which you can be here. Okay, now there are the name character functions like substring. Like if I want the substring from N1 to N2, for example, like extracting some substring part from a string. So it is like A, B, C, D, E, F. I want from 2 to 4. So you will get here like B, C, D. Okay. So B, C, D you will get here. This is the substring function. Then graph function, like search for the pattern in X. If fixed false, if you get that, then the pattern is a regular expression. If fixed is true, then the pattern is a text string. So return matching indices, like whether you are you have got the match like pattern matching or not. Then other than that, like for example, like A, C, B, A, C, you are getting at the A at the second location. Okay, so if it is true, it will then pattern is a text string. Okay. Then sub pattern replacement, X ignored case false and text false. So find the pattern in X and replace the replacement text. If the text is false, then pattern is a regular expression. Otherwise, this is a pattern of text string. So this is the same. Like slash slash s, I'm passing the pattern hello there. So in that case, you will get it hello there. This is basically we have set it like we can say text is equal to false. So then it is going to be the regular expression. So you have added the dot in between hello dot there. Then string split the element of the vector character vector X as split, like a string is split like A, ABC is divided into the A, B, and C. Then paste, like for pasting, like if you want, as the name denotes, like concatenate function we used to use in C and other languages. So similar to that, paste is there. Paste x 1 is to 3 separated by 3. So x1, x2, x3, and this is separated by the double quote. Similarly, you have the x 1 is to 3, like then and separated by m. So this quotes will be replaced by the m. So xm1, xm2, and xm3. So this is the way it is going to work. To uppercase, which you have already used to convert the string into the uppercase, to lowercase to convert it into the small letters. Okay, now the most important thing. Okay, so this is the basically we can say the core of the R programming, the statistical functions. Statistical, if you have already done the basic stats and the advanced stats, so in that basic stats you have in your syllabus, there for which already the VCs are there in your past session. So in that case, statistical function, what we do in that, mean, median, mode, then range, others. So these all are the statistical functions. So for that, we don't need to basically calculate it or design the whole function for this. Like we already have the inbuilt function in the R programming. So mean, like which will give you the mean value, you have to pass the complete vector over here. Median, it will give you the median value. Mode, you all know all of these functions, so I don't think so there is a need to explain that. So then you have the function for the standard deviations, also the calculating the variance also. So all of the statistical function, you have the inbuilt function over here. So you can easily go through that this unit. So this is just the explanation of some of the mathematical function. Maybe you all are already aware with that, so I haven't completed it in a very elaborated way. Through your SLM, you can easily get it. Okay, just like I'm going to start now. Here is the unit 5, which is called the graph. So graph, which is again the core feature of the R programming language. So in that case, what happens, like everything, because we are working on a very large data set here in R programming. So it is not possible actually to basically go through the whole detailed information. Many a times when you execute uh, any of the project in R, you have the complete data set. So in that case, complete data set you cannot understand. So maximally, like we represent all of the information in the form of the graphs and plots and charts. So in that case, that is the main core of the like our programming language. We have different variety. Like in Python also you use the ggplot, and in R also I can use the ggplot. So there are various inbuilt packages are available in R, which provides us the flexibility to create the graph and the plot as per our requirement. So here, like we do have the like understand the R graphic system, visualize the data into different plots and graphs. Okay, so here how we are going to create that. For example, I have the Fibonacci series. So Fibonacci 1, 1, 2, then 3, 5, 8, 8, 1. So I'm going to plot Fibonacci graph. So in that case, I am using some of the parameters, lots of flexibility is there. I'm just using the sample over here. Plot X with this you get your simple graph. Then plot X is equal to Fibonacci. Main, the title you are setting, you specify the title using the main argument. Sub, the subtitle appears here. The X lab, the X axis lab is X lab, and the Y axis lab is X lab. So how does it will appear? Like this, for Fibonacci series, you have the plot here, like 1, 1, then 2, then up to 3, then 4, and this is the plot I have. So whatever parameters I have set, the main heading is you specify using the title, using the main argument. The subtitle will appear over here. This is the Y axis and this is the X axis. So this is the way you can represent your, like we can say, plot your graph over there. Then other than that, I am using it with some variation, like the main, the first 7 Fibonacci numbers, okay, heading, then position in the sequence on the X parameter, then position, then the Fibonacci number is here, then plane, font size we can set here. So font mean I am setting 1, plain text for title, then I am setting it 1, normal size for title, then I am setting it for bold text of numbering. Then finally we are setting the gray color for the flag labels. Okay, so this is what, like these are the parameters which we can set. So when we start we will start using it. So in that case, we can draw the plot as per our requirement. Okay, another one plot like which we use commonly is the histogram. So histogram is what? It is executed with the function hist x, which will give you the base histogram. So here I am using it with some variation, which is giving me the AFL margin of 2010. So this is what, like, we can say x is equal to ALF margin is my data set. Main data frame, sorry, main, okay, just okay, this is my ALF margin. So in that case, I need to find out like how many times like how many times we get the 20 points, how many times we get the 10 points, how many times we get the less than 10 points, and there are overall we can say there are the 33 games total. So in that case, like, it is very difficult to understand and find in this form. So we convert it into the histogram, like the basic histogram I am preparing here. Main, the title you have said, you said the X lab, you said the Y lab, then other than that the destiny, sorry, density will be 10, and angle like 40. You will have the shading lines of the 40 degree, border gray 20, color gray 10. So you will get all these inbuilt values. So in our studio, what we do, whenever we are writing a function, automatically parameters keep on appearing. So you don't need to remember all these parameters what you are passing over there. You just type the first letter and you will get the solutions over there. So this is the way we can plot the graph. Sorry, histogram. Then we are using it with some other variation like histogram, ALF margin. So this is what I have got here. Panel A. Okay. Other than that, I have the stem and leaf plots also, box plot and the scatter plots and the bar plots. So stem will give you like in the form of the stem we can get like the minimum value and the maximum value. So this is what I am using the stem ALF. So 11, how many times it appears? This appear at 6 times, then 10. So it will be 10, 1, then 104, then 108, then 9. It will be 94, 95, and 98. So this is the way it appears. So 0 will be 0 times. So how many times it's appearing? That will be get it with the stem command. So here we have the box plots also, which we use generally use. Here we have the scatter plots also. Here I am using the linear regression over here. So like if you are calculating the my sleep hours and my grumpiness, then you can use the scatter plot. If you are basically getting the parenthood dance sleep and parenthood grumpiness, then you can have this type of plot. So similarly, if I linear regression I usually use whenever I am basically finding out the sale of a product depending upon the sale of other products. For example, if I need to predict like during like if the sale of the milk is increasing, so obviously the sale of the bread will also and eggs will also increase. So that demand can be represented with the help of this linear regression and with the help of these linear scatter plots. Yes, with this unit is also over. If you have any queries, so I am going to conduct the OSI sessions also today. So you can discuss questions with that. You can mail me your queries on this ID also.